Hi Nandana. Yeah. Should we start?
Yes, sir.
Okay. Okay. So today we start from circular polarization, and then we look into little bit into broadband patch antenna, and then MIMO, how to use it for MIMO patch, and and what are the characteristics of MIMO situation scenario. We'll look into that. So first thing is, so far we are looking into the other characteristics of patch antenna, like input impedance and the bandwidth efficiency, all this. So the another important factor of patch antenna is polarization, right? If you remember in our initial days, we are discussing the characteristics of antenna. So one was polarization efficiency, right? So what it says is uh, how much the transmitter and receiver polarization is matched, right? So, now we have to discuss like why polarization is so important. Why do we need a circular polarization antenna? Why can't we see if you design a normal patch antenna, it will be most likely a linear
Linearly
polarization.
polarized.
Yeah, yeah. It will work only in Y plane, E plane, or H plane, not in both.
HP.
So now the question is why is it important, right? So because most likely the antenna will be used for communication, right? Why do we design antennas? It's for some kind of communication, right? So if the transmitter antenna and the receiver antenna, if their polarization does not match exactly, there will be lot of loss due to polarization mismatch. So that is how we calculate polarization efficiency, right? So to get rid of that, most of the times maybe our transmitter is here and receiver may be a lot of far away. So we don't know
Hello.
ourselves. Yes.
Sir, it was not clear. Can you repeat? S-
You
The
can hear
receiver
me,
was.
right?
Yeah, yeah, yeah.
Okay. So I am saying,
Mm,
let's say the transmitter antenna is fixed somewhere, like the
uh,
base station or the mobile
mm,
phone towers, right?
mm, mm,
And the receiver antenna, it might be far away somewhere, and that may not be fixed, right? It can be moving or something.
Moving also.
Let's take the antennas inside our cell phones, right? So
Mhm.
that every time we are no moving our phones away from here and there, we cannot tell the user to keep the mobile phone like this fixed, like some
Mhm.
position, right? That we cannot do. So if that is the situation, then how this phone, our mobile phone, will receive? There will be lot of polarization mismatch, right?
Yeah.
Until like unless the transmitter antenna that has a circular polarization that will transmit in both planes, both E plane and H plane. So if that
Okay.
happens, then what receiver, whatever the location or like the alignment of receiver antenna, it will not matter that much. So that is the case. Okay, right?
Okay. Yeah.
Understood, right?
Yes. Yes, sir.
Okay. So there, the alignment of the receiver antenna and transmitter antenna will not matter that much if you have a circular polarized antenna.
Polarization.
As,
So,
exactly.
in order to eliminate this polarization mismatch, we are using circular polarization.
Yeah, this is the one
Uh,
of the reasons. Yeah.
reason. Okay.
So now the question is, how do we make the normal
Polarized.
antenna circular polarized? Right? So if you remember, the characteristics of circular polarization was it should have two orthogonal
To
components, right? Ex and Uy both,
yeah,
and they should have equal amplitude, right?
amplitude, phase
And also
difference of 9.
exactly. So the thing is like, so all these three conditions has to be satisfied.
Mm-hmm.
So now what you see that normal patch antenna, if you just feed at one point, what happens? The electric field, the normal the dominant transmitted field will be in only one direction, either in E direction, E
Yeah.
plane, or H plane, right?
Yes.
It will be like that. If you have feed at only one point,
Mm-hmm.
right? If you see in the rightmost picture, this is the TM010 mode, right? That is the
Mm-hmm.
dominant mode we generally, have in our patch antenna, right? Rightmost, the top rightmost picture, right?
Waveguide.
And you see the across the length, the cross section across the length, it shows the fringing field, which is the, there is this red circles, red curves that comes out of the patch. That is the fringing field, right? And
Yeah.
there is, you see, in the both sides of the length, there is a blue arrow coming out of this, right? I think
Yeah.
maybe. So that is actually the direction of, the transmitted electric field. That blue arrow, it shows it is across the length, right? So that is why our, remember, the E plane should be across the length, should have across the length and also in the direction perpendicular to the plane, right? That is what we saw before. That was the plane of E plane. Because the actual transmitted field is in the direction of this thing, these blue curves. Okay.
Okay.
I mean, the blue arrows. Yes. So if that is the condition, so that means the dominant electric field will be there in the E plane, and which has the direction of these arrows as well as the direction perpendicular to the plane of patch antenna, right? That is the E plane. Yeah. So now what happens in this situation? It becomes a linear polarization antenna, but we need another plane perpendicular to this plane, right? Because this is, let's say, this is EX. Now we need another EY also for circular polarization, right? So how do we get that? Then we should have another hit point in some other point so that this TM001 mode is also excited, right?
Okay.
Now if you see in the TM001, right.
So a single antenna with two feeds.
Single antenna,
Or
we are
no.
going towards that, but
Okay.
there are other options. I'm
uh,
telling you what
okay.
is the, reason behind it. Okay.
Okay.
Yeah. So the thing is, like, we need two different horizontal or orthogonal electric fields at the far field, right? Yeah. So here, if you take only TM010 mode, it will have only E plane field. Okay. Now, if you go to TM001, you see that, electric field configuration changes completely, right? So here the fringing field will be in opposite direction. So it will be across the width, not in the length like the previous case. So now you see there, like now in two orthogonal direction, electric field will be generated. If we can somehow produce both these modes or excite both 010 mode or 001 mode, that is what we need, right? But now the thing is, like, not the condition is what we need two orthogonal fields, but there is
Of
another
same
condition.
amplitude.
Same amplitude, that you will be almost same if you excite at with same electric field, right? I mean, with same current or same voltage, if you excite, it will be like that. But the other condition is what?
Phase difference of 90
degree phase. So how that will be done? So that will be generated by how you feed or excite these two modes. There should be 90-degree phase difference between these two excitations.
Okay.
So this is the logic behind it. Now you have to see how you can do this. These two defined modes you have to generate and excite them at 90-degree phase difference, right? So for that, people have started with this defined kind of scenarios. You see the leftmost one, top leftmost. So there they feed with a single feed is divided through two lines, and then they feed at two, two vertical positions. So why generally, in TM010 mode, we feed at across the width, and for 001 mode, if you see, we feed across the length. So that is exactly what has been done here. Okay, at two different points across the length and width, both they have connected the feeds. Yeah. Do you see the first one? Right.
Means a left figure.
Yeah. First A. Picture A.
Yeah. Okay.
So yeah, now the thing is, you see there is a lambda by 4 line extra.
This is a square patch, no? So, so square patch and a rectangle patch will be different, no? Along which?
Square patch. Yeah, right. So that is the same, right? I mean, it does not matter much. So only the frequency will be like this. So you see, even that thing is also crucial. If your length and width are not same, the excitation will E and H field will not be same, right? Their resonant
Same.
frequency has to be same, right?
Mm-hmm.
We want the polarization at same frequency, right?
Oh,
If you
okay.
see normally our length and width are different, so TM001 and 010 mode frequencies will be different, right? Because it has 1 by L and 1 by W proportion, right?
Mm-hmm.
Remember? If
Yeah.
they are not at the same frequency, then how you can have the same polarization at the
Polarization.
same excite, right? That is why the
Okay.
square patch,
Mm-hmm.
right?
Okay.
Yeah. So now you tell me why this lambda by 4 line is required extra. You see this power divider?
It's a quarter wave link transformer. That is the
That is
for the
right,
impedance
but
matching.
no. But when
No.
in our polarization, why do we need it?
Polarization. Uh,
See, there are three things,
for the
right? Yeah.
for the phase difference.
Exactly. We need a
Yeah.
90-degree
Okay.
phase
90-degree
difference,
phase
right?
difference. Okay.
Yeah. So that is how we generate. Lambda by 4 means it will generate 90-degree phase difference.
90-degree phase difference. Yeah.
So here we feed or excite these two modes with a 90-degree phase difference, right?
Mm.
Even the same case happens with the B also. Picture B also, it takes a hybrid coupler, 90-degree hybrid branch line coupler. So this branch line coupler also does the same thing. It generates two different power sources with 90-degree phase difference. So
Okay.
it does the same thing. Okay. So if you read this paragraph, it says actually the same thing what we are discussing. So the circular polarization is obtained by two orthogonal modes and excited with a 90-degree time phase difference between them. So that is what we are discussing. And for a square patch element, so easiest way to have circular polarization is to feed the element at two different adjacent edges, so that we can generate TM010 mode as well as TM001 mode.
TM001. Okay.
And the other thing is the quadrature phase difference is obtained by feeding the element with a 90-degree power divider or 90-degree hybrid coupler. Okay. So that is the main concept. Right. Now there are other structures also how you can do. Instead of two different feeds, how can it be done with only one single feed? Okay. So you see here this picture with only one single feed, people have generated circular polarization. Okay, but here although the main theory remains same, that we need to generate two different feeds and two different orthogonal electric fields at 90-degree phase difference. But how do you excite those two modes? So the main concept, you have to excite two different modes, two different orthogonal modes. So people have also discussed or looked into different ways. So they say instead of feeding at two different the center nodes of two different adjacent points, you feed at the some diagonal points. If you do that, people have seen that this will also generate the two different adjacent modes, right? Because this mode, if you see, like the previous case, here you see, here the feed was at two different center points of the adjacent sides, right? So instead of that, they are feeding at the corner itself or diagonal corner itself, right? So people see, if you do that, it will excite those two nearby modes also. Okay. So this is what they call orthogonal degenerate modes. You see, if you read there, it says if you feed the batch at a single point to excite two orthogonal degenerate modes of ideally equal amplitudes. Okay. So this kind of feed can generate those two modes. Why degenerate modes? Because it is not exactly the same mode. It will be nearby frequency. Okay. So here there are a lot of calculation what should be the length and width, all this accordingly. And see the right side picture, it shows. So where should you feed exactly? Instead of a microstrip line feed, if you have a coaxial feed, what kind of thing you should look into? That it shows here. Okay, right side picture. So idea remains same. So only thing is now the question is how do you have two orthogonal modes excitation? So there are many other papers also available in literature. So if required, you can look into it. But the main idea remains same like this in the air. You should have both TM010 and 001 mode excited. Okay. Either these modes or you can also go to higher other modes, but it should be orthogonal. Like 020 and 002. They are also orthogonal mode, right?
Orthogonal. Okay.
So orthogonal in the sense the electric field they generate, it should be orthogonal. So only thing is you have to now ensure how do you do this. Okay. So that is there, and all this you can read into this. In this paper, it is quite old. You see, 1981 paper. And okay, so we'll go into next one. So next thing is
So will I get this recordings after the class also? Means after this
yeah.
term?
Can you access it? I think it should be available now also. You try
It is
once.
available now, sir, but I'm asking if we are ending this course, no, after that we will get or no?
Yeah, it will be there. It will be available there.
Okay. Okay, sir.
Yeah, I think so. Otherwise, I don't know. It might have some time limit. Okay, maybe 1 month or 2 months. After that, they the
Oh, it will be
Microsoft can.
automatically.
Yeah,
Okay.
you better download it or something.
Okay.
Yeah,
Yeah.
it might be not there forever. Okay, like 1 month or
No.
2 month time limit should be there.
Okay.
Okay. So the another interesting or important point is broadband antenna, right? So generally the the constraint of microstrip antenna or what is the limitation is we have, although
Narrow
it is
band.
yeah, it is single plane, it works everything very fine and beautifully. You can integrate you with other circuits and everything. So point is it is very narrow band. So people have looked into like how to make it broadband, right? So before that, let's see how the bandwidth is calculated. So generally we calculate is as normalized bandwidth or fractional bandwidth. So the formula is the fractional bandwidth formula is FH minus FL by FR. So what is this? This is the FH is the, you take a center frequency, FR is the resonant frequency or center frequency. Around that, what is the higher band, higher frequency, and FL is the lower band. Okay. So you take that difference divided by the resonant frequency. That is fractional bandwidth. Generally, in the papers of microstrip antenna, you will see people report bandwidth like 15%, 10%, 5%, 20%. Okay. So this percentage is calculated like this. Is understood, right?
Yeah.
So, yeah. And there are many methods used generally to increase the bandwidth. So first one is like increasing the antenna volume. So the thing is like people see that if you increase the substrate height, okay, instead of one single substrate, you can take multiple substrate. There that is called stacking. Okay, stacking of substrate. That is one case. Also, people have seen like you can take air gap in between. That is also one way of increasing the antenna volume. So if you increase antenna volume, it increases the bandwidth. So this is accomplished by geometry changes which increase the volume under the patch by increasing the thickness.
Thickness of
So
the substrate.
exactly, yeah. So and also decreasing the substrate dielectric constant. That is another reason. You can increase if you go towards higher dielectrics, like you go see there is a range. Air is one, right? And you the like 10 and 12 is something like I think alumna or something. That is this range dielectrics are available. Okay. So generally, if you use deutoid or FR4, they are around 2 or 4, right? Dielectricity. The lower you go, the more the bandwidth. So
Bandwidth.
if you use air gap, so that is why it increases the bandwidth, right? And also because air gap sometimes is very difficult to get because it cannot be integrated with other device, right? With this much problem. Generally, people take sometimes thermocol and other material. That is also having dielectricity almost close to air, foam and other materials. Okay, thermocol foam. That also people use as a substrate. So these things they increase the bandwidth. And there are other regions, other things, right? Including using a matching network and also perturbing the antenna geometry to create or relocate resonances using short and slots in the antenna. So this perturbation we will look into now. Just saying if you modify the antenna geometry somehow, they can be used to increase the bandwidth. And the broadbanding of microstrip antenna is often accomplished by increasing the thickness of microstrip antenna. And there are problems, right? Because whenever you increase the thickness, what happens? There will
Inductance.
be the inductance increases because you have to feed these things, right? Many other
Length will.
times, yeah. So this probe feeding will be required many of the times, coaxial feeding. So if you increase this gap, the length of the probe increases, right? That increases the inductance. So that is one problem. So we have to somehow manage that. So let's see what are the other things people have used. Yeah.
So one doubt, sir. By adding the slots in the antenna, how this bandwidth is improving or increasing?
Yeah. So that is
Means,
why I'm coming. So the
okay.
problem, so see, we saw that somehow we have to increase the volume, right? So how do we increase the volume? By including some air gap or some kind of gap,
Some
right?
substrate.
Substrate, yeah. But the problem it creates is that it increases the inductance, input inductance.
Because of the prob. Okay.
So that's why they are saying that there will be a problem in driving point impedance. There will be a mismatch. Understand, right? Because the
Yeah.
feeding length increases, now there will be a problem in impedance matching. Your S11 will not be good anymore. Although you can
Okay.
get a good bandwidth, but your
Bandwidth.
S11 is
Oh,
hampered, right?
okay.
So that is why they are saying that we need a now proper matching network. The matching is required to have a better S11, right? So that is why we are coming to how to compensate this inductance, extra inductance.
Okay.
So this is the thing I think you are talking about, right?
Uh-huh.
Yeah. So these are like you see how old these things are. The first paper were this improved compensation in 1987 paper. You see.
87.
Yeah. So see, people have worked out in long time back. So why they are saying? Let's see what is it here. Use of very thick substrates leads to an increase in the inductive component of the input impedance. That is, it is obviously we can see that, which ultimately prevents a match being obtained. So we do not get a proper matching, or Z in should be close to 50 ohm, right? That is what we want for matching. But because of this inductance, it does not happen. So the solution is introduce series capacitance to cancel the inductive reactance. Okay. Which appears at the driving point. In the driving point means what the feed is actually there. That is the driving point. So there we have to introduce some series capacitance. So how do we get this capacitance? That is why we use this slot. If you cut some slot in the metal and these two sides of the metal and inside we have some dielectric. So that is how capacitances are, right? Capacitance means, right? There is two metal and in between we have a dielectric.
Dielectric.
Right? So that is how we generate a series capacitance by these slots. So researchers have used a rectangular or circular slot surrounding the feed probe. There you can see the left picture. You can take a circular slot, and there are also what called rectangular slots also to provide the series matching capacitance. Okay, and another approach is the right one. The right one they do not cover the whole the excitation point, but just one side of the cover, one side of the excitation point, they cut this slot. So see, it is provide series capacitance to a place, a narrow slot directly in front of the feed point, and adjust its length until a match is obtained. So this, there is no formula or whatsoever. Most of these things is like you have to adjust these things and see when the match is obtained. Okay. So, but the main intuition or the logic behind it is that we have to get a capacitance to balance the inductance because of the long feed. Okay.
Okay.
So that was this thing, and Okay. So maybe you can look into this book. This is quite good book. The Microstrip and Printed Antenna Design by Randy Van Krop.
Randy. Okay.
Next we'll look into MIMO concept. So give me 2 minutes. I'll come back.
Yes. Okay.
Okay, so we'll start again.
Yes.
Okay, so now the point of discussion is MIMO. Okay, nowadays you see there are many discussions or all the next generation communication schemes are like on MIMO, because I think 4G onwards we are using MIMO, even
Mine.
now current 5G, and the next 6G people are talking about massive MIMO. So what is this MIMO all about? So MIMO abbreviates for multiple input, multiple
Multiple
output.
output.
So in our all of our mobile phones, if you see, there are like multiple antennas, right? There are maybe 5, 6, or 7, 8 antennas in there. So why there are so many antennas? So many of these cases, what happens if we have multiple transmitter and multiple receiver antennas working together simultaneously, it can increase the data rate
Okay.
or capacity. Okay. So, okay, yeah, just give me, yeah, okay, just give me a moment. Yeah, yeah, okay. Something have came here.
Okay.
Okay. So the objective of MIMO is that if you have multiple transmit and multiple receive antennas, it can give you many advantages. Okay. So you look into what are these advantages. The main concept is transmitter has multiple antenna as well as receiver. And in the picture you see there is the channel in between. What we call channel means the environment in between through which the waves will propagate. Okay.
Okay.
So what we
These are the
call
scatters, no? So, in
is
the
that
real
this
life environment. Okay.
exactly, yeah, yeah.
Mm-hmm.
So that is what we call generally channel in communication.
Mm-hmm.
It's called wireless channel.
Wireless
Okay.
channel.
Hmm. So the objective is acquire higher information rate and overcome constraints of expanding traffic. So the thing is like the newer the generation of communication, like from 4G to 5G to 6G as we go, we need to have more and more data rates, right? That is the target of these things. So like now we are going towards like some 100 gigahertz of 100 Gbps of data rate in 5G, and maybe next will be far more or something. That is what we are targeting, maybe towards that. So how do we get this more and more data rate all the time? So one way is to get multiple antennas so that we can do this kind of generate. How that helps, that we'll look in. Another is like there are more and more number of users into coming there, right? That's why the
Mm-hmm.
traffic is too much nowadays. Traffic means the user traffic. So how to accommodate all this traffic? That is another concern for the our service providers. And what happens previously, what we are doing using in previous generations, mostly we had firstly the phone services, call services, as well as SMS and all. Then came the other internet. So with internet, initially we had what normal Google searching and all this, and other WhatsApp and Facebook and all these social networking apps. It came later, but the more advanced it becomes, there are many wireless media applications nowadays, and like we are now talking about IoT, right? IoT means Internet of Things.
Internet of
So
Things.
exactly. So what happens that there are many things which are connected over internet, and they will automatically manage each other through sensor and others. That is what we look into. And there are now several cameras and the other message navigation on GPS functionality, right? All of these are mostly connected towards internet, right? So what happens? We need a very fast information transfer nowadays. So how to have that? So the one concept it has came is the MIMO. Okay. So conventional antennas it face multipath and co-channel interference and interference mismatch. So if you have only single antenna or something, it will have many problems like this. If you have only single antenna, it will go through this many reflection and transmission through the multiple, multiple obstructions in the path, right?
Mm-hmm.
So that will lead to this multipath phenomena as well as interference among the defined paths. So what people see that the main concept is if you have only one single antenna, so they will go through these problems, multipath and all. So there will
Uh,
be errors in the
Probability
data.
of. Okay.
Exactly. What you said, this that is
Uh,
how the probability of bit error,
which.
right? Bit error, right?
Mhm,
That increases.
mhm,
So people now say if you have multiple antennas instead, so and let's say you transmit this data through all these antennas together. Okay,
mhm.
multiple antennas through that you together transmit this data. So then how will it affect it? So what happens is the same thing is the concept underlying is that if you have multiplicity, right, there will be less number of error. Understood, right? So thing is like let's say you are sending the same packet multiple times,
Mhm,
and over the time you average it, right? It will reduce the probability of error. So
mhm,
here also the same thing. The same data, if we send through multiple antennas, all of them will go through some kind of error and all. But because we are sending multiple times, and if we take
The
average or
chance
some,
of okay.
yeah. So it is like that only. So it's the same thing is like, I am now talking to you. If the same thing I tell you multiple times in multiple slides or like half an hour, I tell you the same, you'll understand it better, right?
Yeah.
Yeah. So here also the same thing. It's called multiplicity. So
Okay.
there we use multiple antennas to send it through multiple times so that the number of error reduces. If number of error reduces, then we increase the high data rate. We can improve the data rate. So this is called, spatial multiplexing. So there are two things here. Okay. So one is, let's say we forget about the data rate. Let's say even with one antenna, whatever error happens, it is acceptable. Okay. So this, if that is what happens, if the error is acceptable with only single antenna, so we can send multiple antennas, multiple data, not same data, multiple data with the multiple antenna. Okay. So if they parallelly we send, then it will increase the data rate. Are you understanding, right? Let's say we have here 4 antennas. So through 4 antennas, we parallelly send 4 data bits, 4 data streams. Okay. Previously, we had only single antenna. We are sending one data stream through this antenna. Okay. Now, if we have 4 data antennas, we send parallelly 4 data streams. So that will obviously increase the data rate 4 times, almost 4 times. Okay. So this phenomena is in MIMO is called spatial multiplexing. Multiplexing means, we do it over different scenario, multiply it. That is why it's called multiplexing. And over it happens in spatially because these 4 defined antenna, the waves will propagate in 4 defined channels. Okay, so that is why it's called spatial multiplexing. Understood, right? So this is one very important scenario. And there is another important thing in MIMO is called spatial diversity. So what is that? So diversity is, diversity is linked to the noise, bit error rate. So let's say, with single antenna, we are getting lot of error, right? So how to reduce the error? So there, if we transmit the same data stream with 4 different antennas instead of one antenna, now we are transmitting all of them same data stream. So when the receiver sees it, it sees many different type of data. I mean, define for the same data stream, it has diversity of the data, received data. Okay. So diversity comes from this multiplicity.
So can you repeat?
Okay. So first we talked about.
Diversity.
Okay. So let me come there. First we
Okay.
talked about spatial multiplexing. There, the multiple antennas had multiple data streams
Multiple
parallelly.
data.
So now we are coming to multiple antennas have same data stream, not different. Same data stream are going through it. Receiver collects all the different data all together, but all of them same data, right? Receiver collects 4 different data streams from 4 different antenna, right? Let's say there are 4 transmit antenna and 1 receive antenna. Okay. Understood the scenario, right? Yeah, tell me what you're saying.
No, sir. In diversity, actually, 4 antennas will transmit same data, and the receiver will receive the same data 4 times. Or is
Same
that
data
right?
4 times. So
Okay.
what will happen? Like now we can this data stream we can form as a matrix, right? So there are this
Okay.
from 4 different antennas we can form a 4 different rows of a matrix,
Oh.
right? If that happens, so these 4 different things are different, right? So that is what brings diversity. Although it gives you the same data, but the receiver will receive it differently.
Differently.
Okay.
Okay.
So from these different variations of the data, antenna can better decode it. receiver
Yeah, so
decoding becomes
probability of error will
exactly.
be reduces. Okay.
Exactly. So these different data streams with the same data is called diversity. So we call it
Okay.
spatial diversity because it
Uh,
happens over different spatial channels.
Spatial channels. Okay.
Uh, So there are these two things. One is spatial diversity, another is spatial multiplexing. Okay. Hmm. So that is the main thing, main characteristics of MIMO. That's the advantage of MIMO. Okay.
Okay.
And all of this you remember all happening at the same operating frequency. All of the different antennas working at the same frequency,
Same
right?
frequency.
Exactly. Yeah. Yeah. So now the thing is like you see this kind of scenario generally happens. It is the multiple transmitter and multiple receiver antennas is there, and all of the antennas have you see the the encoder and modulator, demodulator, decoder, all these things. Whatever we have the chain of the communication, it happens there. So see in 5G, people have talked about highlights are multiple polarization and high data transmission over 1 GHz. That is what have been proposed, right? So around more than 1 Gbps data rate has been proposed, and high acceptable increase in bandwidth. So people also are trying the band. I mean, increase in gain. Sorry. So people are also trying to increase the gain of the antenna so that that will also affect the bit error rate. If you have more gain, obviously the bit error rate will be reduced. So that's why it is vital to increase the gain of the antenna. Right? That is why people use arrays, right? Phased array
So
and all the
MIMO is also an array concept, no?
MIMO is
Multiple
also array
antenna.
concept. Hmm. But
Yeah. Okay.
the MIMO, how it is defined to phased array, you tell me. Is phased array is also MIMO?
Uh, no.
Yeah. So how it is defined? In MIMO, what happens? You see all these defined antennas. They all have some kind of port coming in, right? You see the data has to be given through all these antennas separately.
Oh, okay.
Do you see this in the picture? All of them has
Uh-huh.
some ports connected to the antennas.
Yeah. Okay.
Understood? That is why it's called MIMO, multiple input, multiple output. So
Okay.
whatever antenna you have, all of them should have a port connected.
Mm-hmm.
Port being coaxial port or SMA port, whatever.
Uh-huh.
But in phased array, what happens? Phased array, there are multiple antennas, but there is only one single port.
One single one. Okay.
Right? So phased array and MIMO is different.
Different. Okay.
Understand? Okay. Phased array, what it does, it can steer the beam. Steer the beam means you can generate in different directions, and also it can give you a better gain. But here MIMO concept is different. MIMO is specially designed for communication.
Communication. Okay.
Exactly. So now, yeah. So now there is some communication equations and concept. So there is the Shannon's, if you know,
Channel
I don't
solution.
Shannon's
Yeah.
law, channel law. It gives you the capacity of the channel, how much maximum data rate you can achieve. That is dependent on the SNR or the signal to
The
noise ratio
bandwidth.
and the bandwidth. So now
Band.
it says in the MIMO case, the formula changes. The changed bandwidth is, where the M is the number of transmitter antennas and N is the number of receive antennas, then the formula becomes like this. Okay. So obviously, yes.
Okay. Okay.
Yeah. So obviously, you see, if you increase the number of channels, it increases the bandwidth. The maximum capacity it improves. Right. So that is the mathematical basis of this. And also, the assumption is that the multiple channels are not correlated. So correlation is like this. If you are sending different data streams and both look same, both becomes alike, then the diversity is gone, right? We want different data to so that we can generate better decoding or we can reduce the bit error rate. So the one vital thing is that the correlation of this data stream should be reduced. So that is why any radiation pattern correlation or coupling between the antenna elements will decrease the performance. So that is how we are coming to there. The characteristics of our antenna design is we should reduce the coupling. If you remember, if we have a multi-port antenna, we should reduce the coupling. So why it is important is because of this. If
It will
there are
degrades the radiation pattern.
not
No,
degrade the
not
radiation, correlation. I told you, no, we need more diversity. That is the main feature of MIMO, right? Spatial diversity. So that the whatever output streams coming in, they should look different.
Different. Okay.
Okay. If you see,
But means one should not affect the other. That's
exactly,
the coupling.
exactly.
Okay.
Okay. So that is there. So because of that, we should reduce the radiation pattern correlation or coupling between the antenna elements, so that this MIMO performance is not degraded. So then what to do? So they're saying designing MIMO antenna systems with good isolation and low correlation between their elements is very critical to achieve high data rate. So we should have a good isolation between the antennas and low correlation between them. Okay. So how isolation is measured? Isolation is measured with S21 among multiple antennas. So generally we prefer a value between below minus 20 dB. Okay. So we are talking about if there are multiple antennas very close, in a very close distance. That is what is required in MIMO, right? Okay. So if that is what you do, then we need two things. One is good isolation, another is low correlation. So how do we measure that? So isolation is measured as S21 between this antenna. S21 is measured like that. If you feed excitation in one port, what is the effect in other port, right? That is what S21. So we want generally below 20 dB S21 to have a good isolation between these antennas. And now we will look into how correlation is measured. See, now correlation coefficient is a very important measure. You will see in many of the papers and other recent works. So how this is measured, let's see. So correlation coefficient describes how much the communication channels are isolated or correlated with each other. So so this will generally measure in terms of the radiation pattern. Okay, the radiation pattern, if these two antennas are generating, how much is the measure of correlation between these two patterns generated by two antennas? Okay, so that is how is done through this correlation coefficient. And this is the patterns. If the patterns affect one another when operated simultaneously in MIMO, because in MIMO they have to be all these different antennas simultaneously used. If the patterns affect each other, then it will reduce the performance, right? That is what we don't want. So you want to see the radiation, the correlation should be less. So now the actual term is called envelope correlation coefficient or ECC. So this ECC formula is, you see, this is the, it's a big formula, right? This is measured as F1 and F2 dot product in an integration over theta and phi. D omega, if you see, D capital omega is the 3D angle, or it is measured as steradian, right? So what is this F theta phi? F theta phi is the 3D field radiation pattern of the antenna. For the antenna, you should know the radiation pattern in terms of theta and phi. Then you can calculate. You see, it is almost looking like the the diversity, directivity. Antenna directivity has the equation like this, right? Yeah. So for that also you need to know antenna radiation pattern. Here also you need to know radiation pattern. So if you remember in signal processing, there is a formula between correlation between different signals. If you remember, so there was like x1 x2 summation of x1 x2 and divided by summation of x1 summation of x2. Right? Like that we had a correlation formula. Here also if you see, it is almost similar to that. In the numerator we have the multiplication of f1 f2 square, and in the denominator we have f1 square and f2 square separately. So same correlation formula is used here to determine. But the problem here is that you see, until you calculate the 3D radiation pattern, you cannot get the correlation coefficient. And getting the 3D correlation coefficient is not so easy. You cannot calculate it. You should either measure it or simulate it, right? There is no equation to calculate it as such for the complex antennas. Okay, because generally people use it through simulation or measurement. So if you go to CST, there are options there to measure ECC. Okay, they give you option to measure correlation coefficient from your antenna simulation patterns, radiation pattern. So ECC measures how independent two antennas radiation patterns are. If one antenna is completely horizontally polarized, other antenna was completely vertical polarized. If this happens, the two antenna have a correlation of 0. You understand, right? See how polarization is also important. So if one antenna is presents radiation pattern in E plane and the other antenna gives radiation pattern in H plane, obviously they will be completely orthogonal. They will not have any effect on each other, right? So they will have a correlation of 0. Okay, that is what we generally want. We want to reduce the correlation or ECC as much as possible. Okay. So the main understanding is that we should have almost orthogonal radiation pattern so that they have less correlation between them. So now see what now people have seen that this radiation pattern based formula, although this is the actual formula, it is very difficult. So easier thing is to do a S parameter based calculation, right? Because S parameter we can easily calculate and measure. If you have to take an antenna radiation pattern measurement in 3D, it will take a lot of time and it is very difficult also. But S parameter, within minutes we can get from VNA, right? So people have looked into a S parameter based formula. So that is what is given in there. So it takes, SII is the between S11 like that, S11, S22, and SJI is between interport effect S parameter like S21 or S12 like that. So if you have all this, you can calculate the same ECC. So what is the acceptable value? People have seen that the correlation coefficient of 0.3 is acceptable in 4G wireless system, and higher than 0.5 is considered bad. Okay, so around 0.3 can be acceptable for 4G. And you see, for highly efficient antennas, let's say about 90 dB or let's say efficiency is above 90%, the ECC can be determined in terms of S21. This formula can be used. Otherwise, you have to go back to the radiation pattern based measurement. Okay. And you see this plot here. This plot shows in the y-axis ECC and x-axis is frequency. So it changes with frequency also. Okay.
So y-axis it is?
Y-axis is ECC, envelope correlation.
Okay.
Okay. It shows between 4 printed antennas. If you have like 4 defined antennas, how this plot will look like. So all of this, it reduces with frequency. That is what you see, right? At lower frequency is very high and then it reduces. And okay, so there are now what is the solution? Okay, these are the problems and how to measure this. So we can quantify how much is the correlation and how much is the isolation. Okay, so here we started here with here. We need for MIMO good isolation and good correlation. So we can quantify now for both of them. Good isolation we know in terms of S21, and good correlation also you can measure either with this formula in terms of S parameter based formula or in terms of radiation pattern based formula here. Okay. So now that we know the problems, how to improve this? So it says antenna isolation can be improved by increasing the physical separation between antennas. If you just keep the antennas at a more distance, it should increase it. It should improve it, but it might not be always feasible, right? Because you see, just in our cell phone, we have a very small space. We have to make a compact device. We cannot just increase the distance between the antennas, right? What are the other options? Using defined polarization for defined antennas. Let's say we'll have one antenna for right hand circular polarization, another antenna in left hand circular polarization, like that. If we can do that,
so that correlation will be 0.
Correlation will be 0. Yeah, not exactly 0. Theoretically, it is 0. Yeah. But in practicality, it will be all different. What are the other things? If the antennas have different frequencies, using filters to reduce efficiency at the opposition's antenna frequency. Okay. If the different antennas work at different frequencies, then it is less likely to interfere in each other's patterns. Okay. So that is one case. And also we can just filter it out. We will get the other frequency out completely using filter. And reducing the ECC between antennas. So if you reduce the envelope correlation, this will also improve the isolation also. Okay. So these are the factors. So generally people now, this is the, active, this is a topic of active research. People, still work into these topics now. If you have a MIMO antenna, generally people work in a, small patch antenna. Like let's say on the same substrate, you have 4 patch antennas. So it can work like a 2x2 MIMO array. So they will have 4 different, ports. So how to design so that these 4 antennas will have less correlation or less isolation, more isolation. So this is also a topic of research nowadays. Okay. So yeah, these things are taken from CST itself. So from the CST, if you go to datasheet, so they will give you these 2 different things. One is mean effective gain, another is diversity gain and correlation from far field. Okay. So yeah, I'll go through this quickly. So see, we have looked into antenna gain, right? Normal antenna gain. But there, what we have done is like we did not look into. We have taken an ideal scenario, right? What happens in the environment or channel we did not consider. We only saw what is the effect of the antenna, how antenna generates the pattern, right? But in the actual normal scenario, what happens? The environment outside or wireless channel, it affects the pattern, radiation pattern, because it is highly statistical channel or it varies with time, and there are many other different scenarios and characteristics of this channel. Okay. If you have studied, this channel is actually it is not deterministic. It is statistical. So it has some characteristics. And it is determined. It is expressed through some kind of probability distribution. Okay, like we can say Gaussian distribution or Rayleigh distribution. Generally, our wireless communication channels are described in terms of Rayleigh distribution. Okay. So Rayleigh distribution is like it has multiple channels and their defined components have Gaussian distribution. Gaussian is normal distribution. Okay. If you see this picture, so let's say our antenna, it generates 2 different patterns. One is V, PV is vertical polarization and H is horizontal polarization. Right? It is almost like E polarization, H polarization. So if these 2 defined components, if they have Gaussian distribution, it will look like this, a bell-shaped curve. Like, bell-shaped. So this is the y-axis is average power and x-axis is the with degree, angular variation. Okay. So you see both this vertical and horizontal, it might have defined power and defined probabilistic curve. Okay. You see their mean and standard deviation are different, right? Because they are probabilistic channel. It is not certain that what will be. So that is how it happens for a Rayleigh-based communication channel, normal communication channel. So people say that because this effective gain is required because our normal theoretical gain calculation do not take the wireless environment into effect. So to take that into effect, this is taken care of. So first you see what is there. In the formula, we first calculate a cross correlation power ratio, XPD. You see, cross polarization power ratio. So this is the power variation between PV and PH. P vertical polarization power and horizontal power. This is the ratio of that. If you have that, then you can calculate the MEG, mean effective gain. So this also takes the integration where G theta, G phi is the your gain calculation in the theta and phi. That is the actual gain what you get from your simulation, right, or measurement. And what are this P theta, P phi? P theta, P phi is this Gaussian distribution what you have. So now you see what is happening? This is not a normal calculation. It has a that is probabilistic calculation, right? So it will be variation. It does if you it gives you with some probability how much this gain will be. Okay. So that is what it says. G theta and G phi is the antenna gain components, and P theta, P phi represent the channel model. So theta and phi is the see like this is the two planes, right? E plane and H plane, theta
H
plane and
plane.
phi plane. Yeah, both are Gaussian distribution. Okay, and you see the other there, the model assumes that an isotropic power distribution over all angles is unlikely. That is what we generally see. Isotropic power distribution that does not happen it for ground-based mobile communication. So Gaussian, what we generally consider is Gaussian distribution over elevation plane and uniform distribution over the signals in azimuth plane. That is what is assumed. So this represents a regular Rayleigh fading channel. Okay, for cellular communication. It assumes Gaussian distribution for only elevation plane, not for the azimuth. In azimuth plane, we have uniform distribution. So that would be this P theta and P phi. So P theta will have a Gaussian distribution and P phi in the azimuth plane will take a uniform distribution. Okay. So that is how we calculate this mean effective gain. Okay. If we have that, then we next will go. See, this is like, although this is like not like you are going to write a code and do, because all of this you will find in your simulation software. CST has all this, but you should know the theory among bit underlying. Okay. This is the last topic. So it's like what is the diversity gain and correlation from far field. So you see the formula what we have seen before, the rho NV is the ECC. In CST they have a similar, but the notations are defined. How they calculate this is taken from CST itself. So they take XPR. XPR is this cross polarization ratio. What we are saying XPD, they are saying XPR. Okay. So then if you need the ratio of PV and pH, you can calculate that. So from that, with this big formula, you can calculate this. If you have this, here you see they take even the P theta, P phi into account. So that means they even consider the probabilistic model of the channel. Okay, not directly, take only the gain. They even take P theta, P phi distribution also here. Okay, so that is what actually happened in our normal wireless channel. In reality, what happens? That is what our simulation scenario is doing. They try to get as close as reality as possible. Okay. So what is diversity? I told you diversity is achieved when the transmitter received multiple versions of the transmitter stream through defined channel paths. That is what I told you, right? If there are 4 antennas, transmit antenna and one single receiver. So it is achieved when transmitter receives multiple, sorry, not transmitter, the receiver receives multiple version of the transmitter stream through defined channel path. So then there will be diversity among this data. If the signals are uncorrelated, the combined signal at the receiver will provide a higher SNR level and better signal reception. Understood right now? Because obviously if they have, these signals are uncorrelated, if they are all similar, it will not be. If they are obviously uncorrelated, then the combined signal will give you higher SNR. Understood, right?
Okay.
Obviously, they will increase the signal level, signal to noise ratio. That will improve the bit error rate. So how do we calculate this diversity gain? This is calculated as this formula, 10 into square root of 1 minus rho envelope. So you see, for rho envelope calculation, you need first this previous formula. If you have that, then you can calculate other thing. Even the last one is multiplexing efficiency. It is defined as from envelope correlation as well as the efficiencies of two antennas. If you know the efficiencies, eta 1 and eta 2 and 1 minus rho envelope, from that you can get the multiplexing efficiency. So for all of this, you first need to get first the antenna radiation pattern, then the P theta phi is the distribution in the azimuth and elevation plane. What kind of probabilistic distribution you are assuming that you should get. Generally, I told you, right? It is the in the E theta plane, we take Gaussian distribution, and phi plane uniform
Uniform
distribution.
distribution.
Exactly, yeah. So from this, and if you have XPR, cross polarization ratio, if you know all this, you can calculate rho envelope or envelope correlation coefficient. From that, you can calculate diversity gain and
It's
multiplexing
again
efficiency.
multiplications.
Yeah. So
Okay.
these papers you can look into if you are, in future, if you are more interested in this multiplexing in CST only, they have referred in all these papers. So these are more.
So in wireless communication, we are mostly considering the SI-NR ratio, no? Means
Yeah.
signal. Why it is so?
Yeah, so see,
Big,
the thing is like, here we are considering only signal to noise ratio, right? So what this noise comes from? This noise comes in the receiver itself. Okay, receiver itself means that in the receiver channel you have, antenna, then it has, the down converter, it has amplifier, all this, right? So all of this will give some noise. It will add some noise. Okay.
Okay.
So because of this, the generally this noise, like thermal noise or something. So this noise accumulates and it affects
Reduces
the
the
signal
signal.
quality. Yeah. So that is what this thing, that this noise does not come from outside. This is on your
These are the
receiver only.
component.
Yeah.
Okay.
But what happens?
Hello.
So they will be affecting each other.
So can you repeat? It was
So yeah,
the
I am
noise was.
saying in the outside actual environment, there will be many signals, like crores or billions of signal, right? So they will be affecting each other by affecting the correlation between, no, sorry, not the correlation, we call it interference between the signals, right? So people take signal to interference as well as noise both into account. So interference between these defined channels or defined signals, all this together. So we need to take both of these into account.
Okay. So, sir, can we tell that? Can we say noise is also a type of interference, or
No. Noise is not
no?
interference. Noise is a different thing altogether. It generates.
Okay.
It is there in the receiver itself, in the receiver chain itself. It generates noise. Okay. Noise is not in the outside world.
Outside
In the
of
channel does not give you noise. Channel gives you interference.
interferences. Okay.
So whenever this receive antenna gets the signal, so there only it starts adding noises until it gets decoded in the whole chain. So everything, all the components, there will be many components, right? All of them add some noise.
Okay.
So yeah, so our class concludes here. Okay. So yeah, okay. So
I
yeah.
have one more doubt.
Okay.
Actually, why this anechoic chamber is of in that shape, which means that pointed shape? Why it is?
So you know, right, why anechoic chamber is required to understand that, right?
It acts as an absorber, no?
Yeah.
To reduce the interferences and from outside, and also reflections from the walls.
Exactly. Yeah, exactly. So, like, now the question is how to absorb this signal, right? So, what happened now? Future people have seen the research is like this. If you have this kind of, pyramidal or tetrahedral shapes, right? So, if you if the signal falls in between, right, they will go through multiple reflections in that shape between these shapes. You consider like there are many 3D shapes there, right? Many pyramidal shapes. So whenever signals falls in between, okay, so there will be reflection in between them, okay. So ultimately, what happens? This the higher edge or the top edge, they are almost comparable to the wavelengths of this thing, so they does not let you reflect, okay.
Okay.
Okay, it does not get reflected. For the reflection, you need a better, smooth surface, right?
Mm-hmm.
If you remember, the let's microwave reflection you cannot see, but light reflection you can see, right? So for
Mm-hmm.
light reflection, which can reflect only a very smooth surface like a mirror or something, that only can reflect light, right?
Okay.
But a normal wall, it cannot reflect. Understand, right? Why
Okay.
it is so? Because for reflection, it is called, the geometry of this surface. It should have the it should be smoother than the wavelength itself. Okay, so whatever
Okay.
irregularities you will have on that surface, it
Mm-hmm.
should be smaller than the wavelength.
Okay. For the light to reflect. No.
I'm giving you example of light. Okay,
Okay.
so I'm saying why the normal walls does not reflect does not reflect light, because light has a wavelength in terms of nano uh, angstrom, right? I think
Mhm.
yeah, I think it has in terms of angstrom, so it is
Okay.
very small, right?
Mm.
So in our walls, what we have, yeah, nanometer, I think, yeah, 750, around 700 nanometer is
50
the,
nanometer.
yeah.
Right down.
So yeah, if you in our normal bare eye, we see our walls are smooth, okay. But if you
Mm-hmm.
see in the microscope, the irregularities what you have in these walls, those are more than nanometer. Might be in
Oh,
terms of millimeter, or maybe in micron. Understand,
okay.
right? If that
Okay.
happens, then it does not reflect. This is the basis rule of reflection. It is in the very old rule. It comes from optics only, optical, uh,
Okay.
optics. So this is light is also a microwave. Not microwave. Sorry, it's electromagnetic wave.
Yes. Okay.
So this theory is valid for all different type of electromagnetic wave, all the way
Oh,
from microwave till ultra X-ray to till X-ray and gamma ray. Okay. So the concept is, for the surface to reflect, its irregularities should be smaller than your wavelength. Now this surface in there, in because what happens now, microwave has wavelength in terms of what, in 4 gigahertz we have around 30 by 4, around 7.5 centimeter of wavelength. Okay, so 7.5 centimeter wavelength. So obviously our this absorbing surface or whatever surface we keep, they should have irregularities of more than that. Then only it will not let it reflect. So that's why you see all this wave. It our anechoic chamber also, it has some length, some bandwidth of where it will absorb. So in the lower frequency range only it matters. In the lower frequency range, the bandwidth, sorry, uh, the lowest range, the wavelength will be higher. Okay. So if the wavelength is higher in that range, whatever irregularities we have, whatever shapes we have designed our anechoic chamber, it should be even more than that. Okay. So let's say
okay.
in generally our anechoic chamber is designed for around 900 above 900 megahertz or something, it will work. So you can calculate
Okay.
easily. It should be more than what would be wavelength in 900. Okay. So
Mhm.
you can easily see that these shapes, the length of these shapes and distance between shapes is even more than this wavelength at 900 megahertz.
Okay.
Okay. So that is how we can say that this surface is having irregularities more than the wavelength, so that it will not reflect.
Reflect. Okay. Okay, sir.
Yeah, and that is one thing. And there is another thing is that it is also coated with carbon or some kind of material like carbon. Huh?
Uh,
So it will
uh,
absorb it. So this is what this will stop the reflection. But after the stops, what will happen? So this carbon material, it absorbs it.
okay.
Okay. So these are the two things it happens there.
Okay, sir.
Okay. So yeah, any more doubt, I will be there anyway. You can ask me anytime in the
Yeah.
offline. Okay. So we'll conclude it here. Okay. Ah,
Okay. Thank you, sir.
okay. Bye. Bye.
Bye
See you
bye.
next year again.
Bye.
Okay. Bye.